Everyone. This was my final project for Photonics class. I'm a graduate student in material science, 2D materials, so I was working on photonics because I do optical characterization of thin film materials. So welcome to my presentation, Calculating the Color of Carbon. In this presentation, I will be discussing a method I developed for determining colors of thin films based on their material properties and the source of light that will be used to view them. Alright, so that may be kind of confusing, but the purpose for this is if you ever worked with 2D materials, you'll know that you need to exfoliate them in order to pick them up and stack with them. That's a whole other conversation, stacking of 2D materials. But when you're looking for materials to stack, you know that you need to find the right thickness. So, for example, graphene is very difficult to see at low thicknesses, so assuming you can see my mouse. Some of these flakes, like this one right here, is very thin. That's probably only a few atomic layers thick. And then if you go over here, it's much thicker, maybe close to 10 layers thick. And then if you go over here, it's very thick. It's probably around like dozens or close to 100 layers thick. And then you can see the color drastically changes. This purple is the substrate, the silicon and silicon dioxide substrate. And that has to do, the color is based on the thickness of the oxide layer. There's some thin film interference that makes it that exact purplish color. So, so depending on what application you're using the graphene for, you want a certain thickness. So let's say you are using a new material and you haven't calibrated your thickness curve, so you don't know what color a certain thickness of material will be. Then you can do that with this tool that I've developed in Photonics class. How do we do that? So, inspiration for this was a paper I saw that documented the transmittance of graphene depending on the thickness of the graphene, and as you can see, there is a negative correlation of graphene layers to transmittance, which makes sense. The more layers there are, the harder it is for light to get through graphene. And so I took it upon myself to simulate this same curve using Tidy3D software, and I was trying to generate the same curve. So I set up a simulation like this with a source plane wave up here, a graphene sheet on a silicon substrate down here. Or no, it's just graphene. So no substrate, it's just floating in midair. And then so the plane wave propagates, comes through here, and then the sensor measures the power of the transmitted wave. And I was able to obtain this graph. So it is a little bit different, as you can see. The formula for this curve, which the paper graciously provided, is this dotted orange line. So you can see it doesn't quite match, and I attributed that to be due to the thin film effects of two-dimensional materials. Like there's some, when they get very thin, the electrons and atoms behave differently than in the bulk material. So the bulk properties are what we were using for these thicknesses, because like a 20 nanometer thick graphene might not behave, it will behave slightly differently than bulk graphene that is cut to 20 nanometers. I hope that makes sense. So there also could have been something I did wrong with simulation, but anyways, it matches very well, and we can move on to the next step of the experiment. So how can you calculate the color that something should be based on the thickness? So we already proved in this slide that we can accurately get the transmittance of a material as it varies in thickness just by simulating it. So what we need to do then is to take the source of light. So for example, the sunlight has an equal-ish, each color contributes equally, like wavelengths. All wavelengths are present in sunlight is what I'm trying to say. That's this orange or yellow curve. And then if you, some other common light sources, white LED light tends to have a peak around blue and then a peak in green and a peak closer to orange or red. So that's what white LED light is made of. So it doesn't, there's not a lot of this blue-green area, and there's almost no purple light in white light. There's also things like a barcode scanning laser is almost entirely red because it's a laser. Tungsten lamps tend to skew more red because they're black body radiation, I think. Anyways, yeah, so if you can input your light source and then calculate the reflectance off of your sample of a specified thickness, then, and this reflectance is at each wavelength, right? So in the visible range, so from 400 to 700 nanometers, what is the reflectance of the material? The reflectance is what you see and how you perceive color. So based on the source, so let's say if it's noon sunlight at 500 nanometers, there's a lot of that wavelength in noon sunlight, and then at 500 nanometers there's a lot of reflectance. So, well, for this specific spectrum or reflectance curve. So for this material here, it's going to look very bluish green because of the high reflectance at that wavelength and the high presence of that wave in the light. Okay, so that makes sense. And then this results in a color profile of the material. So as I was explaining, you kind of just multiply these curves together and you get the color that the material will appear to a viewer, which I think is super cool. Yeah, and you can even do that if you really want to do this. You could do this for like animals that can't see visible light. You could like predict what a flower will look like to a bee if the bee only sees infrared or ultraviolet light, right? They see ultraviolet. Anyways, yeah, you can do this for any wavelength. So for example, look at this. So I calculated using a 285 nanometer thick silicon oxide layer, which is the same as the silicon substrate I have here, silicon dioxide layer I have here. I calculated what a bare substrate should look like and got this color. So this color should match this color here. And I also calculated what 100 layer graphene would look like on top of the substrate. So something like this maybe is about 100, maybe. And then so I said, okay, purple and purple, it all looks purple, but I really want to try to get this like greenish yellow color. So then I simulated 200 layers thick, and look at that, it spat out exactly what I was looking for. And this is about, I guess, 200 layers, something like that. But you can see here, I extended these colors so you can kind of compare them. And I think it's incredible that I was able to get it to change from the purple color to this gold yellowish color that we see in real life. So the conclusion is this works. This certainly works. You might say, well, these colors are not really close at all. Like this bare substrate, it should have been easy to get the bare substrate right. And it's because this picture was taken through a microscope of which the light source we aren't sure of, or at least I wasn't when I was making this presentation in the crunch time I had. So I modeled it with sunlight. So I modeled these colors I generated them by assuming sunlight was incident upon the flakes, which it certainly is not. But I think it's close enough because sunlight is basically white, might be a little more yellow. So clearly this phenomenon where you get this this kind of yellowish gold tan color as you increase the graphene thickness is present, and that just proves that this is like a credible way to do this. So in the future, if we ever have a new material, yeah, and then the other thing is we can verify with AFM if we really need to get the exact thicknesses. And then for other materials, let's say we need to exfoliate something that's like 10 nanometers thick, we don't know what color that's going to be, so we could simulate it with this software first, with this tool, and then say, okay, this is what we're going to be looking for. And it can be on any substrate. You just need to plug in the substrate to the simulation, and you can do it. And I think that's super cool. Thanks for watching.